Okay, this is a very classic work energy problem. What we have here is a particle, which is launched vertically with an initial speed of v0, and we're asked to determine the maximum height h obtained by the particle, assuming that air resistance is negligible. Okay, so since we're looking for a change in position given a speed, we know this is going to be a work energy problem, and since it's a kinetics problem, I want to always have a free body diagram. So if I sketch the free body diagram quite simply here, I'll simply have the force due to weight. So this is a conservative force, and so we know we don't have to worry about that apart from potential energy. Speaking of potential energy, it's helpful in these problems to define a datum, so let's go ahead and choose the ground to be the state where Vg is equal to 0. Knowing that, I can say that the initial kinetic plus potential energies plus the non-conservative work done in moving from state 1 to state 2 has to equal the final kinetic energy plus the final potential energy. In this case, I can solve for each term. So T1, because the particle initially has speed v0, will simply be 1/2 times m times v0 squared. I'm going to add to this the initial potential energy, which since it's at the surface of the ground will simply be 0. There's no force here, which contributes non-conservative work, so U1 to 2 non-conservative will be 0. At the maximum height, the particle will actually be changing direction, so it'll instantaneously have 0 velocity, so T2 will be 0. And V2, the potential energy will be solely due to gravitational potential, so I'll have here m times g times h. If I go ahead and substitute these 5 expressions back into the work energy equation, what I'm going to have is that 1/2 times m times v0 squared is equal to m times g times h. At this juncture, I can go ahead and cancel out the common m, and I can solve for the h, and in this case what I'm going to get is that the maximum height obtained by this particle is equal to v0 squared divided by 2g. A very classical result. You'll note that the mass of the particle doesn't matter here. Why don't you think about that for a minute? Why might that be? As you think about that, I'll bid you adieu. Have a great night. Take care. Bye.